Welcome back to class 16. Here's example 411 out of Bernanke. We have an insulated 2 cubic meter tank, this insulated tank, and it contains ammonia. Ooh, you don't want to be around this thing. 40 degrees Celsius, and it has a quality of 2%, so it's a saturated. It said that. Oh, excuse me. The vapor is withdrawn, so sticking it out of the tank. So this is the transient process part of the thing, until it reaches 10 degrees Celsius for some reason. And we assume the process is adiabatic. Well, that we could because that's an insulated tank. And the only vapor leaves. That is that there's no liquid leaving. And we want to. So our goal, your mission, should you choose to accept it, is to find the mass withdrawn. Sometimes I'm clipping this thing out of a textbook, and they've included sort of the answer. Not really. There's a lot to it. I wrote a lot on my page, so this is going to be. I'm not sure this is going to be a great one or not, but we'll see. We'll see what happens. So anyway, the temperature at 1 is 40 degrees Celsius. The temperature at 2 was 10 degrees Celsius. The quality is 2%, so we can look that up right away, of this ammonia. And where our goal is to find the change in mass. So I'm going to go to table B.2.1 where we have ammonia, and at that temperature, 40 degrees Celsius, we note that the saturation pressure, because it's just good, is 1,554.9 kPa, which is just quite a lot. Because they told us the quality, we know that we need to be going here, and so we will find V1 and H1, and while we're at it, let's find U1. All right, so let's just say that we did it, because you don't need me to write all this out. So there's a 0.003353 cubic meters per kilogram. You could look it up and do this and use the quality with the HF and the HFG. I mean, the VF and the VFG and so forth with each of these. I got 1,000. Why did I write that over there? Oh, I see. Okay. My bad. I think I might need to know the gas. No, I don't think so. I think we're okay. So we went 393.4 kilojoules per kilogram. And the internal energy is 388.2 kilojoules per kilogram. While we're here, let's also go at T2 equals 10 degrees Celsius and know that the Psat, I don't think I need to know that, but we're going to write it down anyway, 615.2 kilopascals. And we're going to get, we don't know, let me think for a second. We don't know the properties yet. Is that true? Yeah. I don't think we know the properties. So we don't necessarily need to do any of those yet. I think I was doing I was jumping ahead of the game. Oh, I see. Oh, this is a stupid problem. Oh, I hate problems like this. All right, so I'm glad I didn't ask any problems like this in the homework. All right, so here's the joke. Here's the gist of the thing. I hit my oh yeah moment here as I'm looking through the thing. You could come through here and write that the V, with this, you could write V2 is equal to, and here's my VF, 0.001600 plus X2, and then here's the VFG, 0.20381, right? So we don't know this and we don't know that, but we might be able, it might be useful to us. I think that's what we're getting at. I mean, and I also have this written down too. So we could do the same thing that we do here. We could write out from the table, and I don't really need this many sig figs, but I went ahead and did it anyway. Okay. So this is unknown what our final conditions are going to be. But we do know that it's going to be 10 degrees. They told us it was 10 degrees. So we're going to guess that it's not going to go into superheat. It's not going to be a compressed liquid, so it's still there. So we take a look at what our initial mass is going to be, M1. And we take the volume, which we're given, and divide it by V1, which we have. Right? So this is... I think it's always going to be 2. So I don't know why I wrote V1 here on my page. So don't be like me, kids. Oops, trying to write only 2 zeros. 3, 3, 5, 3. All right. So you get the original mass. That's how much mass is in it to start with. I don't know why I waited all this time, but let's write down the conservation of energy, or just it's still the conservation of energy. We are still accounting for the energy, right? So it's going to be M2U2 minus M1U1 equals Q minus work plus M in, H in, M exit, H exit. Right. So we only have mass going out, so that's going to go 0. We're going to say that the thing is insulated, right? Does it say it's insulated? It's adiabatic. That's good enough. There's no moving parts. And anybody else? Well, except the conservation of mass, we have M exiting is going to be equal to M1 minus M2. Right, so we can plug them right there. Conservation of mass, conservation of energy, used in conjunction. So when looking at this, what we're left with is M2 plus M2 U2 minus M1 U1 is equal to negative, because that's what the sign is, negative M1 minus M2 HE. Distribute the M right into here and then collect, and what you'll find, you'll get an M2 U2 minus HE. It's going to be equal to M1 U1 minus HE. If you see that right there. And here's the joke that they're doing here. All right, so we're going to take this right here. We already have M1, we have that value, but we don't have M2, but we do know the volume, right? So we can go V over specific volume times this. And did we make everything negative for some stupid reason? I think we did. We decided to multiply both sides by -1. And so we went minus U2 plus HE equals M1 minus U1 plus HE, just to be jerks, apparently. And let's see. So we put in the value here. We have the value for this, and we have the value for this. Why do we have the value for that? How do we know we have the value for that? HE. We say, oh, I know. Oh, no, this is the one I really hated this one. All right. So this is not a problem that you could figure out on your own. They decided just to play around, do like a silly mind trick, and I kind of hate this type of thing. What they decided to do to fix HE is to come up with this. This is since only vapor is leaving. Since only vapor is leaving. Man, I hate this. the Hg is all we need, right? So the exiting Hg, the H here, because they made this say that only vapor leaves, all right, and this Hg, it could be different for these two different temperatures, right? At 40 degrees and at 10 degrees. So it changes. So how do we find that He? We decided to take the average of the two Hg's at those two states. See, I told you I didn't like it. So you'd take Hg at 40 degrees Celsius plus Hg at 10 degrees Celsius, and you take the average of them, and that's what you say that He is going to be. Man, I don't want to do this any longer. I wrote a whole lot of shit on my paper page to be able to do this thing. But anyway, so what that allows us to do is, because we have this number, and we have this number. Like, we're able to find these. Like, we could look these up, just like when we were up here doing this stuff, and that's, I forgot why we were doing it. Up here, I could also get that I could also get Hg, right? These were all the values at this 2%, but we can also get at this temperature what the gas enthalpy was going to be. So we get that to be 1,470.2, I think, kilojoules per kilogram. And then we also have the Hg's. This is the Hg, call it Hg40. We go to Hg10. Somewhere in here, I think I got it 1,452. Right, so kilojoules per kilogram. So down here, we could take this one plus and that one, take that one half of it. We could take and say that He is going to be the average of those two. Unfortunately, they're not that far apart, so 1,461 kilojoules per kilogram. All right, so now that we have these values, we can go ahead and put them into place. So, okay, I went ahead and I divided out over here. I went ahead and divided this by V. Divide this by V, right? So that cancels out. Divide that. All right. So here's my, and I have a value right here that I could bring out right in there, and I could make that negative and subtract from it. I can also, because I have two equations right up here, I can solve for that x. Do you see the strategy now? The little joke thing that they're doing. So let's go ahead and work the thing out right here. I'm going to take this value over here. That's the 1461. And then I'm going to subtract out minus what I have up here for U2. So you have 225.99 plus x2 times 1099.7. Brackets and brackets, divided by, and then go for the V up above. Yes, 0.003353. What I got away from me. Plus x2 times 109. No, sorry. I was looking at the next line up. Next line down. 0.2038. Is that a 1? Sure, put the 1 in there. Who gives a shit? And we set that equal to this thing, which is a value, right? So we have the mass. Kind of getting in the way of my thing here, so I'm going to come down a little bit, shift down a little bit, cheat. I'm going to cheat, you big cheater. And this is going to be, let's just go ahead and write this one first. 1,461 minus U1, which is all the way hell up at the back right there, 388.2. And then divide by volume, which we were told 2. All right. And so we can solve for this. We can just isolate this x2, do a bunch of algebra. I swear I did it, right? So I got 0.01092. You don't believe me? Right here. See, I did it right there. See, I did the math, worked it out. Boom, boom, boom. And I got this. And then once you have this, you can get this specific volume, right? We can find the specific volume from this quality, and the quality wasn't much, right? It was like 1%. Barely made it. 1%, but then we could divide and we could find out what the mass is, what the mass 2 is, right? And so the difference between the masses is how much mass left us, how much went away. This was a terrible problem. I guess I don't know. Okay, so let me take back. This, I suppose, this has like some real world applications, but it's not. I don't like it in terms of an example for students, because I think you would turn your brain off somewhere along the way. Like you just wouldn't think to do this. But as a practical matter, this might be a way, that somebody needs to estimate how much they just lost, and they don't have something like ammonia, like maybe in a chemical plant, and they've lost some, and they don't know a way to like find out how much they lost in this tank. So they use temperature as a means of trying to identify it. So in that ways, maybe there is some amount of pragmatism for this. But I think I'm not going to do this one in class either. I didn't like the previous one. I don't like this one. I'm going to do these last two, I think. Yeah, these last two. So these are going to be problems out of the book. I think out of our book, because I don't think I saw any in single that I really liked for this topic. So we're going to do some examples from that were meant for class 15, and then we're going to do these other two examples, and that's going to be it. So this was recorded for posterity, though. So glad we recorded.